In this video, we're going to take a look at exploring the latest dataset from Global Fishing Watch in SedonaDB and Whereabouts Cloud. Global Fishing Watch is a global nonprofit that does some really interesting data analysis using a lot of satellite imagery and satellite radar to detect sort of what's going on at sea with offshore infrastructure and especially vessels doing fishing. They do a really good job of publishing data products as a result of their analysis. And we're going to take a look today at the latest project, which did analysis using satellite imagery to identify offshore infrastructure structures and also industrial vessels that were then tied to the public tracking system to identify whether or not the vessels identified using satellite imagery were properly publishing their location information through this public tracking system known as AIS, which can be an indication of possible illicit fishing activities. So this data is public. I'll drop the link in the video description. We're going to download two CSV files, one with information about offshore structures, one that has information about vessel observations. Then in Whereabouts Cloud, I'm already signed in to Whereabouts Cloud. If we go to the Files tab, and if we look in the data directory, this is the Whereabouts file browser where we can upload data. I'm going to navigate to this directory, which is specific to my Whereabouts user. So any data that I upload here is going to be private to my Whereabouts user. You can see I've already uploaded a lot of data in this Global Fishing Watch directory, including the two files that we're going to be using. So if you haven't yet, you can go ahead and create a free Whereabouts Cloud account and sign in and start the notebook environment. And we've started a new notebook here. I'll be sure to link the code for this notebook also in the video description. So let's go ahead and import our dependencies. We'll configure the Sedona context, and then we'll also paste in some URLs for those files from S3. So if we go back to the Whereabouts file browser, and if we navigate to our data directory, we can see where those files are just by copying the S3 path using this icon for those files, or also for the directory. So one of these is just a root directory of where we're going to be saving some data. So let's start by loading the offshore infrastructure file. This is the smaller of the two. I think there's just over 1 million observations in this data set. Yeah, 1.4 million observations. And you can see the data that we have. We have the position of the structure, the classification label, the date it was observed, and then a unique ID assigned to the structure. Now, because we imported from a CSV file, we need to explicitly cast all of the types, if we have numerics or dates, or in this case for the location, we're going to use the stPoint spatial SQL function to convert that to a geometry. And if we do a group by label, we can get a count of the number of different classification labels. Looks like the most common is oil, so like an offshore oil drilling rig. We have just over 500,000 of those in the data set. Now, this is a time series data, so we have observations for the same structures over time. If we just count the distinct IDs, we can see there's just under 40,000 distinct structures, which is a size that we can visualize to get an idea of the spatial distribution of these different structures. First, though, let's simplify the classification labels. So there's a confidence score associated with the different classifications. For simplicity, let's combine the possible and probable into a single category, oil, wind, or unknown, just to simplify our visualization a little bit. And then we can use the Sedona Kepler, this is the Kepler GL integration for Sedona, to visualize this data by just passing the Sedona data frame and giving just a name for the visualization. Now, one thing that's nice about Kepler is that we can interactively style, filter, and work with our visualization. So let's change the fill color to be based on the label classification. And instead of this color ramp, let's choose something that has more unique colors, something like that. So we can clearly distinguish the different classification labels. And here we can start to explore the data to get a sense of the spatial distribution of these different structures. So, for example, we have what would appear to be a lot of oil structures on off the coast of Africa here, quite a few also in the Gulf of Mexico. We can see also where there are a lot of wind structures offshore as well. There's going to be kind of the bright fuchsia ones here. Cool, so that's quite interesting. Let's take a look at the industrial vessels data set next. So we'll go ahead and load that into a data frame. We can see we have a few more fields here. We have things like the length of the observed vessel. Remember, this is coming from satellite imagery, and then some machine learning models are applied to determine whether or not these are fishing vessels. And then also they're compared to the AIS public tracking system to determine whether or not this observed vessel was transmitting its location information. So we can see we have just over 23 million observations in this data set, so a little larger than the other. And again, we'll also need to explicitly cast our types here since we are importing from a CSV where by default, there's no schema associated with that. So everything comes in as a string. So we use the stPoint function again to create a geometry and cast into our numeric and date values. We can do a group by for the matched category just to get a sense of the distribution on the different categories, whether or not they were matched to, again, vessels that were transmitting data properly to the AIS public tracking system. And we can see that there are over 9 million vessel observations that were unmatched. So these are potentially vessels that may be doing some illicit fishing activities. Now, again, this is a time series data set, so we may have multiple observations of the same vessel over time. So if we take a look at the count of the distinct vessel IDs, we can get a sense of how many unique vessels we're working with here. And we have just over 500,000 distinct vessels. Now, we said this data set had 23 million observations, which is quite a bit to visualize every point observation. So a common approach for visualization would be to visualize aggregate data. And a good way to do that is using H3 hexagons. So we're going to use two H3 spatial SQL functions here, one to get the cell ID for each location observation, and then get the actual geometry for that cell ID. So H3 is a spatial indexing method that covers the surface of the Earth in hexagons of various resolution levels. So here we're using resolution level 2. We can change the size of those for more fine-grained indexing. Now, what we're going to do is get a count of the number of vessel observations within the area of each hexagon and then visualize those results. I've excluded a few cell IDs that, just because of an artifact of how the map projection works, they're kind of distorted. So we're excluding just a few there. And again, in Kepler, we can go ahead and configure our visualization. Let's use the fill color based on num. So this is going to give us a color ramp showing us where we are observing more vessels. Now you can notice that at more extreme latitudes, the size of the hexagons are distorted. This is a result of the Web Mercator map projection. So typically for a choropleth map like this, we would use a equal area projection. So let's see how we can use GeoPandas and Matplotlib to visualize the same data, but using an equal Earth map projection. So we'll convert our Sedona data frame to a GeoPandas geodata frame, and we'll specify we want the equal Earth projection and then visualize that. So this visualization preserves the size of each hexagon to help us interpret that spatial distribution a little more accurately just by looking at the visualization. Now, so far we were looking at the count of all vessel observations. Let's filter now just for unmatched vessels. So these are vessels that we believe to be not properly transmitting their location to the AIS system, which is going to be an indication of possible illicit fishing activity. So we'll create a new Sedona data frame, and we will use GeoPandas to visualize this data. This is a little bit different visualization style. We're converting to Web Mercator projection because we're going to use the Contextly package to bring in these country map tiles to have a base map here so we can have an idea of where the different hotspots are relative to countries throughout the world. And we can see here that there appear to be some hotspots in Southeast Asia, along the north coast of Africa as well, for possible illicit fishing activities. One of the really exciting things going on right now in the geospatial world is the adoption of GeoParquet. GeoParquet is a method of specifying how to store spatial attributes in Parquet. And there's a large number of folks in the community that are working to adapt the standard. It fairly recently, a few months ago, had a 1.0 release. You can see the specification on GitHub and follow along with some of the discussion. It's specifically for working with vector data. And basically, the specification says that geometry should be serialized as well-known binary in Parquet, and also that the bounding box of all the geometries in a Parquet file should be stored in the column metadata. So we'll take a look at how the benefits of Parquet can be applied here. Parquet is really known for providing efficient data storage, so taking advantage of encoding and compression to reduce the file size, send less data over the network at query time to result in performance benefits there. And then also for efficient retrieval by chunking the data so that at query time we can request a finer grained selection of data to evaluate just what's needed to resolve our query. So to compare the efficient storage size here, we're saving data as GeoParquet and also as GeoJSON, and then we'll compare the file sizes. So these will take a few minutes to write these files to our S3 location in our Whereabouts Cloud account. Okay, so our GeoParquet file is done, and now we are saving the same data as GeoJSON, and then we will compare the file sizes to see how much we're saving in terms of storage by using GeoParquet. Okay, so now that that's done, let's go into the Whereabouts Cloud file browser and take a look at the relative file sizes. So first of all, our initial CSV data was 6.1 gigabytes. If we take a look at the GeoJSON file, we can see that's 9 gigabytes. So GeoJSON is not known for its efficiency on disk, so that's to be expected. If we look at the Parquet file that we wrote, it was 2.4 gigabits. So from 6.1 gigabytes to 2.4 gigs is some significant savings. So that's an efficient file storage, taking advantage of the encoding and compression built in to Parquet. The other benefit of Parquet we mentioned was efficient retrieval. So being able, thanks to chunking of the way the data is stored, being able to take advantage of only accessing data that's needed. Let's take a look at how we can take advantage of that using a spatial filter performance comparison. So I drew a polygon here, roughly capturing the Gulf of Mexico. It's represented by this polygon in WKT or well-known text, and then we wrap that in a ST within predicate to have a spatial filter here that represents the bounds of the Gulf of Mexico, roughly, approximately. I just kind of freehanded that. So let's time applying this spatial filter to our data, first using our CSV-backed data. So this is going to include the time to load the data from CSV, cast the values to geometry numerics, and then apply this spatial filter without an index. And we can see this takes about 18 seconds to tell us there's 200,000 vessel observations within this polygon. Let's do the same operation this time for our Parquet file that we wrote just a few minutes ago, and it takes 5.2 seconds. Now, this is faster for a few reasons. One is the file size is a lot smaller, so that's less data to load, but also the data saved as GeoJSON, saved as GeoParquet, the geometries are serialized as well-known binary, so we don't need to explicitly cast and process converting latitude and longitude into geometries. We have those geometries serialized there. So significant time savings there. Now, a common approach when dealing with Parquet is to partition a Parquet file across multiple files based on the value of some attribute. We can do this using, say, like an administrative boundary for geospatial data. If we don't have a administrative boundary, which in this case we don't, we can use a spatial index. So previously we saw the H3 hexagons. Another similar index is S2. S2 is a similar idea of cells and resolution level. So we'll add a column here for each row. So for each vessel observation, we'll determine what the S2 cell ID is at resolution 2 for that. And then instead of saving a single GeoParquet file, we're going to partition multiple GeoParquet files by the value of the S2 index. So this will give us a partitioned GeoParquet that we're saving, and then we will compare the performance of querying the same spatial filter using our partitioned GeoParquet and see what the difference is. Okay, so now we've saved our partitioned GeoParquet data. Let's create a new Sedona data frame loading from the partitioned GeoParquet and apply that same spatial filter. And we see this one is 2.2 seconds, which is significantly faster than the 5.2 and the 18.1 seconds earlier. So why is this one so much faster? Well, we said that each GeoParquet file includes the bounds of all of the geometry stored in the file. And so Sedona, when it queries the partitioned GeoParquet file, is able to inspect each GeoParquet file to determine whether or not the bounds apply to the spatial filter being applied. So it's able to skip loading lots of different files and zoom in on just the GeoParquet files that contain observations that are roughly within the bounds of our spatial filter. So then filtering out fewer rows, resulting in much faster query time. So that's quite neat. So we've seen the benefits of being able to efficiently store data, efficiently retrieve data using GeoParquet. Another advantage of GeoParquet is integration with different tools in the ecosystem. So there's a really interesting visualization library from the folks at Development Seed called Lonboard that uses GeoParquet and also GeoArrow. GeoArrow is a specification that's being developed alongside GeoParquet that specifies how to store geospatial data in the arrow in-memory columnar format. And this allows us to very efficiently move data from tools like a GeoPandas data frame into the GPU to render large-scale visualizations, which is quite neat. So this notebook I'm running locally, since with Lonboard, we need to move the data into the GPU in our web browser. So we're going to see more benefits if we're running a notebook locally than if we're running in a cloud notebook environment like Whereabouts Cloud. But let's see how this works. So we'll import GeoPandas and Lonboard, and then I've saved that GeoParquet file locally. So we'll read that into a geodata frame, and we'll take a look at the data stored in that geodata frame. So that loads, and we can see we have our point geometries, which we've loaded from the GeoParquet file. That's great. Now let's go ahead and filter based on matched and unmatched vessels here. So we're going to want to visualize vessels that were matched, a different color from vessels that were not matched to the AIS public tracking system that can be indicative of potential illicit fishing activities. So we're going to create two layers here, one for our unmatched data, which we're going to color green, and one, or rather red, and one for our matched layer, which we're going to color green, and then apply both of those to our map object. So this takes a few seconds to load, but what's going on here is that we're loading and rendering the entire data set. So this is the 23 million points that are being rendered all at once. So this gives us smooth panning, since everything is rendered for our entire data set, and smooth zooming as well. So we can really zoom in here and visualize all 23 million observations, which is really impressive. If you've tried to visualize large-scale data in a Jupyter Notebook before, you may have crashed your notebook before you get to this point. So this is really impressive, taking advantage of the benefits of the GeoParquet GeoArrow ecosystem, which is really quite exciting. Okay, so that was a look at the Global Fishing Watch public data in SedonaDB and Whereabouts Cloud, and also a look at using this data with GeoParquet. I've uploaded both these notebooks to GitHub, and I will share the link in the video description. Be sure to let us know in the comments what type of tutorial content you'd like to see for working with SedonaDB in the future, whether it's certain kinds of data sets or different types of geospatial analyses. Well, thanks for watching. Cheers.